Hello, here is our last lab walkthrough video of elementary statistics, lab 13 on linear regression. So let's get into it. The objectives of this lab are simply constructing linear regression models. So what is a linear regression model? Here's how we're going to think about it. We got two numerical variables. Oh, I don't know what that is. We got an x variable and a y variable. They're both numeric. And we want to figure out what's the relationship between the data. And if we're going to try to plot that with a line, that's what we call linear regression. So linear regression is we're trying to estimate a line of best fit for our model. So the fancy term for what I just described is bivariate data. That means two variables graphed on a scatter plot. So let's take a look at some example data. We got x1 and y1. Will be the horizontal data, y will be the vertical data points. And so each point, we got 5.1. So we got 30 is the x point, 5.1 is the y point. And so the first question is, what direction does this graph look like it's going? If I were to map a line onto it, it's like it's going up. This here. So that's the first thought. Just what's the shape of this data? What about this one? Let's make a plot of this data. Let's say plot x is x2, y is y2. We got a different data set. What's the trend of this data look like? It looks like it's going down. Okay. So here's a third data set. You do the same thing. Tell me what you notice. All right. So what we're going to do with this data set is we're going to analyze something called the correlation coefficient. It's denoted R, and it's a way we can find out how strong a relationship, strength of a relationship. Strong relationship means it maps really close to the line. So here's an example of strong relationship. Each point looks like it fits exactly on a line. We would call that strong. If each point roughly looks like it could represent a line, that would be a weak relationship or relatively weak. And then if there's just no pattern at all, that would be no relationship. Okay, so the correlation coefficient is a way we can measure this. So the function we're going to use is core for correlation, and we got some parameters. Pearson is the method, and we're going to use all the observations. Sometimes we would remove potential outliers, and it looks like we got a 0.96. Notice this value is pretty close to 1. 1 means a strong positive correlation. So we would say this is a pretty strong correlation here. Comparing it to our graph for the first one, yeah, it looks like they fit pretty well on a line. Okay, so that's what we got for data set 1. Let's now find the correlation for data sets 2 and 3. So for data sets 2, we would say correlation x equals x1, y. Is that what we said? Yeah, y. I'm just going to copy this. I'm going to be lazy. And it's just some, look, I'm going to use y2 and we'll x2. Looks like we got a negative value. That means strong negative correlation. It means the slope is negative. They're inversely related is another way to say that. Means one variable goes up, the other goes down. Okay, so you can do that and say what you got for plot 3 as well. And just note, when we got a correlation coefficient of 0, you get something that's close to 0, basically between positive a half and negative a half. That means we got basically no relationship or very weak relationship. Okay, so that's what we'll do for data set 3, see what you get as well. And then we can talk about what linear regression models look like in R. R as well will find the model for you, and we're just going to use this function Lm along with a way to add a line to the plot. We're going to add the linear regression line, the line of best fit. So here's our code that does this all for us. Lm means linear model, and we're going to put in a formula. What goes in our formula is the y variable, which is the dependent variable. Then we put a little tilde, squiggly sign, and then our x variable for the independent variable. And always remember it goes x and y, and we read y versus x, and that's where the y tilde x comes from. That's how we graph something. That's kind of the pattern behind all that. And then we can plot it. We can plot the same points, but AB line says, hey, I'm going to add this line that comes out of my model. So let's look at what all that does. If I run just this line here, notice I generated something called linear model data 1. It's got a lot of stuff in it, most of which we won't use, information about this model. But one of the big takeaways is we can use that resulting model and we can use it to plot a line. So if we just put the model in there, it knows to say, hey, here's the line. Here's the line of best fit. So you can see it's strong positive correlation. And it looks like I did the same thing again. Now, we can also find out what the equation of this line is. So lines, you may know from algebra, look like this. Y equals mx plus b. M is our slope, b is the y-intercept. So the slope, b is where it crosses the y-axis, and the slope, m, determines if it goes up or down. So that will maybe what you see in algebra. We're going to use in this class looks slightly different. B naught plus b1x. That'll be our line. But actually, it's the same thing. Notice my slope here is just b1 and my y-intercept is b0. So we've just renamed the variables for reasons that make more sense when you take higher level statistics classes. It has to do with adding more terms to my equation. Suppose I want to add, I don't know, more terms here. Then I can say b1, b2, and so on. So the way we can find out what these variables are, b1 and b2, is we can run the summary function on our linear model data, a linear model object. So it says, here's our formula, here's all my residuals. Talk about those next. And then what we really want to look at are the estimates. So here we got, that's my estimate for b0, my y-intercept. That's my estimate for b1, my slope. And so embedded in there is that information along with some p-values. That's testing the hypothesis that b1 and b0 is 0 and b1 is 0. So if you're curious what the p-value says, we have strong evidence that these things are not 0. That's what those hypotheses, those p-values are testing. And then, so that's one way to get our coefficients for our model. The other way is to just say this, coefficient linear model data 1. And I already did that. So this shows us here, what's going on? Why is it looking so funny? This shows me that if I want to write my equation, it'd be y equals negative 20.09. That's my y-intercept. And then I would say 0.718 times x1. I'll write it like that. y1 is equal to negative 20, and that's my slope. So let's find the regression line. So that maps the line that we found here. Okay. Let's find the line for data sets 2 and 3. So if we want to use the linear model data set 2, did we do that already? No, we got to do that. We got to find linear model of data set 2. So I'm gonna copy paste that code if I can find it. Sorry for jumping around here. Here's the code I want. I want that data set. Here we go. So instead of x1 and x2, I'm going to change them x1 and y1 being 1. I'm going to change it to 2, linear model data 2. And if notice this object here, I changed to 2, so I want to change it here as well. So now let's plot that. There's our regression line for linear model for data set 2. And then let's find the actual equation itself. So for that, we'd say coefficient of linear model data 2. And that tells us, hey, I got an equation for y2 is 16.49 minus 0.002. So it's a small number, small slope, but it's still very, very, it fits the data pretty well. So you can do that for data set 3 now. And when you're done with that, take a break, pause the video to do that. When you're done, we'll go on to residuals. So residuals are a way to analyze the deviation, how far away I am from my best fit line. So this distance right here, that's my residual. Residual. So each of these data points has a residual. If I look at that vertical distance between my point and my line of best fit. That's what the residuals are. And let's look at how to analyze them. Of note, when we find these residuals, we want to make sure these are randomly scattered. If there's any kind of systematic pattern, that shows that a linear model is not the best fit. That shows there's more going on that our model is not describing. And so here's how we describe what a residual is. We take our data itself, and it's the fit plus the residual. So another way to write it is the residual is the difference between your fit and your data itself. Oh, and one more observation. If your data point is above the plot, if we take data point minus a point on the line, that's going to be positive. Up is positive. Here it's below. If I take point minus line of best fit, it's going to be negative. So I'll draw it this way. If our data point is below, that's a negative residual. Let's go look at our example from data set 1. Here's some code that creates the residual plot. I'll explain this. Par MF row, this is a fancy bit of code that says I want to make 2 graphs side by side. Here's the first graph, or line of best fit as before, and the second plot takes my data set 1 residuals point. And then I put a horizontal line of 0 there. So that second plot here, this is the plot we did previously, it's just squished. It's a little wider. The second plot plots those. I lost it. Okay, we'll try that again. Okay, so the second plot here describes the residuals. So I'll highlight this for us. What's going on here is this point right here, we can't really see it, but it's vertically above the line of best fit. I want to make this bigger if I want to make this bigger. You can really see what I'm talking about. Okay. Here we go. So you can see it's a little better. This point right here, if I were to continue the line, it's vertical, above my line is best fit. This distance right here corresponds to what this distance is right here. So our residual for that point looks like about almost 4 away from our line of best fit. Here's the residual for our second point. looks like it's about 3 away. So notice since it's up, it's a positive. But if I look at the next point, here we're below. So those are negative distances. We're going to go that distance below. Then this point, it's quite a bit below, so that shows a lot of error. And then this point right here is above. So you can see how those residuals show how far away the graph is deviating. And so as far as I can tell, this looks random. If it's random, that means we have a good fit. That's one of our assumptions, is we want the residuals to be random. So do we see any systematic pattern of this? I would say, whoops, that shouldn't be there. There's nothing there. Do we see any systematic pattern to this plot? Based on what we saw, I would say no. No systematic pattern. Okay. And that's important when we're setting up our linear model. We want to make sure that's one of our assumptions we're going to make, is that we have to show our residuals are random. So let's do the same thing for data set 2 now. So instead of doing x1 and xy2, let's do x2, y2, linear model data set 2. We're going to use the x1 points and the linear model data set 2 model residuals. So again, inside this linear model data set 2, there's all this stuff, the residuals we're going to look at. So let's look at that graph. Okay, you see all the residuals here. The deviations from our line are plotted here, and they look random, so that's good. So how many data points have positive residual for this example? I would say looks like 2 have positive residual because they're above. 2 are positive, 3 have negative. And I would say there's no pattern to this. It looks kind of random to me. That's how to answer these questions. So you can do the same for data set 3. If you need to see that, we're just changing x2 to x3, y2 to y3. We're using our linear model data set 3, which you should have made in the previous problem. Okay, so last question of this video is we're going to look at this special data set that doesn't fit our conditions. So let's run our linear model data for data set 4, and let's plot it. Plot it this way. Actually, I'm going to plot it with the residuals because I'm going to do that. So we're going to use data set 4 for this. I'm going to put it on one plot so we can see it all together. Look what I'm seeing. Look at this data. The data looks like it's some kind of, parabola or something. So the line, yeah, it goes through it, but what's really a problem is I can see a pattern in the residuals. The residuals start negative, they become positive, and they go negative. So this is a real red flag. This shows me I shouldn't use a linear model here. There's probably a better model than linear. I'm not keeping my assumptions of random residuals. So there you go. That's just an intro to what we can start to do with linear regression and some of the assumptions. There is a deeper dive in part 2, but that'll be bonus extra credit. It describes in more detail how to describe these patterns as if we're estimating them. And we'll go deeper in analyzing some residuals for the second part, but that'll be bonus. You can do it on your own. We finish this, we'll call it good for the semester. Good work. Let me know if you have questions, and good luck studying for the final. See you soon.